In this lesson, we'll discuss the theoretical underpinnings behind the regression algorithm. We'll start the discussion with the background and motivation to regression modeling technique. Next, we'll discuss the types of data employed in the regression modeling. We'll also discuss in great detail the cost function, that is ordinary least square method, which is widely employed to fit the regression line. Next, we'll discuss the simple and multiple regression modeling techniques. Next, we'll examine the key assumptions behind the classical linear regression model and implications if these assumptions are violated. We'll also discuss the BLUE, that is best linear unbiased estimator properties associated with the OLS estimators. Lastly, we'll briefly cover the role of normal distribution in hypothesis testing associated with regression modeling. We'll also discuss some non-linear functional forms that can be suitably modified to linear functional forms. In this video, we'll provide the background and motivation for the application of machine learning algorithms in business applications. Many times on Amazon and Netflix, we get recommendations for movies and TV series as if some human person has examined and carefully vetted our history of TV or movie watching and provided these recommendations. They are extremely accurate. Also, you would have observed the spam filtering application on your mobile text messages and email applications. If you carefully examine these filtered messages, you would find almost 95% to 99% accurate messages and emails that are like phishing emails or bulk mails which are targeted to bulk audience and not very genuine mails or messages. Also, if you go to website like Google News, you will find news items clustered and put together in groups as if somebody has carefully read these news items and put together similar news items, putting together these news items for our ease of reading. To summarize this discussion, in modern day business applications, for example, Amazon and Netflix movie recommendations, filtering out spams, medical prognosis based on previous health records, algorithmic trading, credit scoring models, these applications appear or are driven by computers without being explicitly programmed. So here computers are learning without being explicitly programmed, for example, in recognizing handwriting, natural language processing, and so many applications in modern day-to-day and business applications where computers are acting as if some human being is working behind the curtains. But obviously, given the volume and nature of data, big data being handled, a human being cannot do these things on their own, and therefore we clearly understand that these are computers working behind the scenes without being explicitly programmed. They are made to learn through these machine learning algorithms. In this video, we'll provide a brief background to machine learning algorithms employed in business applications and finance. Let us start with a very interesting supervised learning problem. In supervised learning, we have a set of input features which are mapped to output labels. Now please note the important keyword here is that output is labeled. So a set of features, input features and output which is labeled. The algorithm is trained using this input output data, and once the algorithm is trained, it is employed in future using these input variables or features to predict the output. A very simple example to this is house price prediction problem, where a set of data, that is size of house in square feet, which is one of the features, and the label, that is house price, is given, and using this data the algorithm is trained. This is called regression problem, where we try to model this using regression. In this lesson we'll discuss the regression problem in great detail, but as a simple example, using this feature which is the size and output label which is the house price, the regression model or algorithm is developed, trained, and for future when the size of a house is given, the algorithm is employed to predict its price. Let's say some new points are given, then this algorithm will predict their price by fitting a regression line, which we'll discuss in detail in this lesson. Another interesting supervised learning problem is classification problem, where a certain label data is given along with features, and then algorithm is trained to classify the new observations across these labels. For example, credit default scoring problem, where we try to classify observations such as loan applications into defaulters. For example, here defaulters are given in red and non-defaulters or good credit borrowers are given in blue. Now we have two features. The labels are defaulter and non-defaulters, while features are net worth and income. Now using the given set of data, we train this algorithm. And once we have the algorithm trained, then as the new data comes in, for example, new data maybe here, using this classification problem, we try to classify the new observations into defaulter versus non-defaulter. Using this model, we try to predict that. We try to classify or segregate defaulters vis-a-vis non-defaulters using the algorithm that has been trained. In the unsupervised learning, the key difference is that the data is not labeled, we have only features. For example, you may have demographic variables such as taste, income, age, and gender, and based on these features, you will try to segregate individuals into different groups. And this is a very useful application in market segmentation by consulting firms who employ such data in creating target segments for targeting them for their products. Such segments are based on this clustering problem, where we try to cluster individuals based on certain features such as taste, income, gender, and so on. So this is a very interesting business problem, clustering problem of market segmentation. Another very interesting clustering problem that we already discussed is clustering of news items depending upon their similarity. So natural language processing and text processing, text analytics applications and algorithms are employed to segregate news items into clusters that are similar based on certain features, maybe genre of news or similarity in terms of geography or the topic of news. They are clustered together by unsupervised learning algorithms that cluster these news items together. To summarize this video, we discussed supervised and unsupervised learning algorithms. In the supervised learning algorithm, we have data which is labeled along with the features, and we try to develop the algorithm by mapping the relationship between input features and labeled output. Subsequently, this trained algorithm is employed to predict future observations or future units. Using their features, we try to predict their output labels. In contrast, in the unsupervised learning algorithm, we have only features, not labels, and we try to map or cluster the observations or units together based on similarity in features. And one of the very important and interesting application we saw was that of market segmentation. In this video, we'll discuss the types of data being employed with machine learning algorithms to train and test the models in financial markets and finance domain in general. In general, there are three broad types of data that are employed in finance domain. First is observations about multiple individuals or units collected over a single period. Second, observations about a single individual collected over multiple periods. And lastly, observations about multiple individuals or units collected over various time periods. We'll examine this and visualize these types of data in subsequent discussion. Have a look at this diagram here. We have three cross sections, C1 at time 1, C2 at time t2, and C3 at time t3. Notice, if you collect only one individual, data about one individual like A, over all the three cross sections, that is 1, T1, T2, and T3, then this kind of data is called time series data. You are collecting a time series of information about individual or unit A. In contrast, if you have 6 individuals or more or less individuals like A, B, C, D, E, and F, and you collect all these individuals over a particular time, let's say T1, then it is called cross-sectional data, because you are collecting all the information about these units for a particular time T1. So it is a cross-sectional data. Lastly, if you combine the time series and cross-sectional characteristics, that is, you collect the information about all the units or individual of interest, that is, for example, A, B, C, D, E, and F, not only for one cross section but all the desired cross sections like t equal to t1 for time t equal to t2 and time t equal to t3, then this becomes a panel or longitudinal data. That means this panel and longitudinal data comprises or involves the characteristics of time series as well as cross section. To summarize this video, we discussed three types of data. First, time series data, where we collected information about individual unit over a given time series. Next, we discussed cross-sectional data, where we collected and analyzed data about multiple individuals or units like A, B, C, D, E, F over a particular cross-section of time. And lastly, we discussed panel or longitudinal data, wherein we combined the characteristics of time series and cross-section. We collected the information about all the units or individuals of interest over multiple time periods, and we call this panel or longitudinal data. In this video, we'll introduce simple linear regression model. Consider a simple linear regression model the way it is presented here: y equal to beta naught plus beta 1 x plus mu. This is often referred to as two variable linear regression model or bivariate regression model because there are two variables y and x. Y here is the dependent variable or explained or response or predicted or regressant variable, while x here is the independent explanatory, predictor or regressor variable. Notice there is an error term or also called mu, which is error term or residual term or disturbance term. This mu represents the aggregation of those factors that are not explained by y. So in this model we are trying to explain the effect of this part on y. Those factors for which we cannot explain or are not part of this model are aggregated or considered to be part of this error term. These are unobserved factors that reflect variables or factors other than x that affect y. Since mu here is also a random or stochastic variable, it is considered that it has some kind of probabilistic distribution. Often normal distribution is employed to model this error term mu. But the idea here is that this is random in nature and its values assume some kind of probabilistic distribution. Beta naught here is the constant term, while beta 1 is called the slope term. This is so because this relationship, this model, can be represented on a two-dimensional space, xy space, where this model is basically a straight line with this intercept or constant term as beta naught, and the slope of this line is represented as beta 1. So this line represents in visual terms this model. So this is a visualization of this model. This simple model aims to study the dependence of y on x, that means how x affects y. Now please note here that regression deals with the dependence of one variable over another. It does not imply simply causation. The idea is that it only establishes the statistical strength of the relation. The causation has to be established a priori by theory. For example, if instead of y, like this, the dependence on y, you replace an x with y and you put it like this, even then the regression model, the mathematical modeling, will give you some kind of statistical relationship, which obviously may be spurious in nature. Take for example crop and rain. Now a priori we already know that crop affects rain. Rain affects crop. Rain affects crop. This is established by our common understanding, common sense. However, even if you put or replace rain and with crop and you try to find some kind of mathematical relationship from crop to rain, the regression model, the mathematical model, will give you that relationship, which is obviously spurious in nature, and therefore a priori theoretical considerations are needed to imply the causation. Now in regression analysis, the dependent variable, which is y, is considered random or stochastic in nature. That means it assumes some kind of probability distribution. The reason is that it also incorporates the effect of all those unexplained or not considered factor which are aggregated in the error term mu, which was stochastic in nature. So those effects or influences will also be incorporated in y, and therefore y is random or stochastic in nature. In contrast, the explanatory variable, which is x, is assumed to have fixed value. That means it is considered to be coming from outside, while y is part of this model and therefore it is random in nature. X is fixed and taken from outside. So the x values are fixed and taken from outside in the model. A closely associated concept here is of correlation. Correlation here establishes the degree of linear relationship between the two variables, let's say x1 and x2. In correlation analysis, both variables are treated in a similar manner and considered to be random. That means no causality from one to other is implied. Let's take for example, if variable x1 moves by 1%, then x2 moves by in the same direction by let's say 0.5%, then there's a 50% correlation between these two variables. However, we do not imply any causality here. To summarize, in this video, we examined a simple linear regression model, bivariate model, where there are only two variables, the dependent variable y, a constant term, independent variable x, and a slope or coefficient term beta1, along with the error term. Y here is the dependent variable which reflects the impact of our model, which is beta naught plus beta 1x, while those effects or influences which are not accounted for by this model are considered to be aggregated into this error term. Now please note, by definition of this model, y here is random and stochastic in nature because it also incorporates the effect of these mu or unexplained part of the model. The explained or modeled part, this here the variable x is considered to be fixed in nature and taken from outside, while y is getting affected by this model itself, which includes the effect of mu, and mu being random stochastic in nature, y is also random and stochastic in nature. This relationship, while it is mathematical in nature and statistical significance is established through mathematics, the theoretical underpinnings or causality from x to y has to be established a priori from theory, not the mathematics. In this video, we'll discuss the role of expectations operator in the context of a random probabilistic variable. Any random probabilistic variable is often represented through expectations operator. This random variable can be the error term or the dependent variable like y. Since these variables attain multiple values, for example, let's take an example of coin tossing game where there are two possible values, and if the coin is fair, then there is a 50% chance or odds for any of the outcome, whether it is head or tail. Similarly, in regression, any random variable like the dependent variable y, if it is assumed to be probabilistic in nature, its expected value is represented as Ey. For example, if there are n probabilities that an event has an outcome of y1, y2, y3, yn with possibilities p1, p2, these are probabilities p1, p2 and so on up till pn, then the expectation of this variable y is defined as p1, y1, p2, y2 and so on, that is sigma py, p is probability, y is possible outcome, pi, vi are equal to 1 to n, where n are the possibilities in the event. This is also called probability weighted mean. If all the probabilities are assumed to be equal, that means many times we do not have any a priori knowledge about possible probabilities. So if all the probabilities are assumed to be equal, then p1 equal to p and so on equal to 1 upon n. And in that case, the expectations is nothing but the simple average of all the possible outcomes of y's. To summarize, in this video, we discussed the role of expectations operator for random probabilistic variables or stochastic variables like error term or dependent variable. We noted that expectations are nothing but simple probability weighted mean of variables. In case we do not have any a priori probability assigned to these outcomes, yi's, then in that case the expected value is nothing but simple average of y. In this video, we'll understand the basics of simple linear regression algorithm with a simple example. Consider the table shown here where family income and consumption expenditures are provided. Here, a population of 60 families is divided into 10 income groups, for example 80, 80 to 100, 100 to 120 and so on up till 260. So there are 10 groups and their consumption, weekly family consumption expenditure, the Y's are also shown. For each level of income X, we try to compute the conditional mean, that is expected Y given X, which is 65. Let us see how this is computed. For example, consider an income level of 80. Corresponding to this income level, a set of family weekly consumption expenditures, that means Y's are provided. So for this given level of X, the corresponding Y's are provided. The summation of these Y's is 325 and their mean is 65. Now this 65 is the conditional mean of Y conditioned upon a given value of X, which is 80, and that is why it is called conditional mean of Y, expected value of Y given X. Recall that in the previous video we said that if we do not have any a priori probabilities of any set of values, we take simple average to compute the expected value, and the same thing we did here by taking the average of these values, which is 65 for X equal to 80. Now the average of all these values is 121.2, and since this value, which is the average of all the values, is not conditioned upon any specific X value, this will be called expected value of Y, which is unconditional mean or unconditional value of Y, because it is not conditioned on any X value, it is unconditioned expected value of Y. Please note that such unconditional value does not account for any income level, that means any value of X, and it is the prediction or expected value of Y or the prediction of Y when there is no knowledge of X. However, one would like to improve upon the value of Y by knowing the value of X if one believes that X affects Y. So if X indeed affects Y, then the knowledge of X would definitely improve the prediction of Y. So if you have the knowledge of X, you can improve your prediction by computing the conditional mean of Y, which is this expected value of Y given X, and that prediction will be more accurate. For example, the conditional mean of Y given X equal to 260 will be 173, which is different from conditional mean of Y when X was 80. Now if one asks what is the best prediction or mean value of weekly expenditure for an income of X equal to 140, then you would tell him that looking at this table, you will tell him a value of 101. That means the knowledge of income level, that is values of X, enables us to better predict the mean value of consumption. So our prediction of Y, which is the mean, improves as compared to the situation when we do not have that knowledge. So this is the essence of regression modeling. So what we are saying here, that for each level of X, we have set of Y values, and the mean of these Y values are joined together. These means of Y values for each level of X, we have expected value of Y given X, and all these conditional means are joined to get the regression line. So this regression line is nothing but the conditional means conditioned upon these X values are joined together to get this fitted line. So for example, if you have the weekly incomes given on X axis, and for each set of income you have a distribution of Y values, this is the distribution of Y values, and we know that for any distribution, if a variable has a distribution, it is stochastic in nature, we can compute its expected value as we have already seen using the probabilities. We can get the conditional means for each given X. We can compute the expected value of Y, that is expected value of Y for each given Xi, where Xi can be 80, 90, in this case 80, 90 and so on. And once we have those conditional means, we can join them to get the regression line. And then in that case, our estimate of Y would be conditioned upon Xi. For any value of Xi, we can predict the value of Y. To summarize, in this video, we said that any regression model of this type, Y equal to B0 plus B1X, Y equal to B0 plus B1Xi, assumes that some variable Xi has some explanatory power over variable Yi, and therefore one can improve the prediction of Yi, the prediction value of Yi, which is Yi hat, can be improved by using the knowledge of Xi. Thus, regression modeling improves the prediction of yi by taking a set of values of xi. For example, if we have the knowledge of xi, the corresponding values of y can be averaged, and this average value of yi for a given I is a better estimate of y. Since this estimate of yi, that is yi bar, is for a given value which is xi, and therefore often such estimate is called conditional mean of yi, that means conditional value of y given x, and this is called conditional mean of y. Another type of expectation of y which is unconditional mean, which ignores the value of x, which does not consider and assumes that we have no knowledge of x, is expected value of y, which is the average of all the values of y irrespective of values of x. It is often considered as per regression modeling that this conditional mean is an improved estimate of y as compared to the estimate of y when we have no knowledge of xi's. In this video, we'll introduce the concept of population and sample regression functions in the context of regression modeling. Recall, in the previous video, we said that if we join the conditional means of y given x, these were the conditional means of y given x. If we join these values, then we obtain what we call is a population regression line. So we join them for each value of xi, x1, x2, x3, and so on. We had a set of values on y, and we joined the mean of these values, what we call conditional mean rather, for given xi. What is the mean of y? When we join these conditional means, what we obtained is called population regression line, which is essentially the regression of y on x. Now, a population regression curve is simply the locus of these conditional means of the dependent variable, which is y, for the fixed or given values of explanatory variable, which is x here. So this is the basic concept of population regression function. The population regression function discussed here can be denoted by this expected value, which we have already seen, expectation of y given xi. This is often referred to as population regression function, fxi. Here fxi is a linear function of x, which is called a population regression function. When we say it's a linear function, this linearity means linearity in parameters, and this can be more simply written as expected value of y given xi equal to beta naught plus beta 1 into xi, where beta naught and beta 1 are population parameters. These are population parameters because they are for the entire population, assuming the population is known, which is a more hypothetical construct. You never have the entire population, but assuming you know the population, then these are the population parameters or the true values of beta naught and beta 1, which reflect the relationship between y and x. Now, when we say this is the linearity in parameters, that means, for example, if this kind of expression is there, where the population regression function is beta naught plus beta 1 square xi, this model is non-linear in parameters and will not be estimated with linear regression modeling that we are discussing here. However, a model like expected value of y given xi, which is equal to beta naught plus beta 1 xi square, this model is, while non-linear in variables, it is linear in parameters beta naught and beta 1. So population parameters are linear, and therefore it can be handled under linear regression models. However, in real life, we do not have the luxury of population. We often work with much smaller set of data, which is called sample. And therefore, what we estimate is not the population regression function, but what we get is the sample regression function. And it is denoted by adding a hat symbol. This hat indicates that we are working with samples. And therefore, the estimated values of y is yi hat. So yi hat is the estimate of population value, which is y. So yi is the population, this yi hat is the estimate of y, which is given with this regression sample regression function, where beta naught hat and beta 1 hat are sample parameters. Unlike the beta naught, which was the population, beta naught and beta 1, which were population parameters, beta naught hat and beta 1 are the sample parameters or the estimators of population parameter, which is beta naught or beta 1. So beta naught here is the estimator of beta naught. We'll discuss some of these estimators. Beta 1 hat is the estimator of beta 1, and these estimators are applied on a given sample to estimate or proxy the population parameters. Using these beta naught hat and beta 1 hat, what we get is yi hat, which is the estimate of y, which is the estimator of population values based on our sample regression function. So SRF, which is the sample regression function, is only an estimate of population regression function based on a given sample or the sample that is available to us. Remember, we do not work with population. We do not have the luxury of population. Now, since this is only an estimate, therefore sample regression function can overestimate or underestimate the population regression function or population regression function values. For example, if you are estimating yi hats and you get this kind of estimators beta naught hat and beta 1 hat, your sample regression function line may look like this. This is one example where actual population regression function is this. So from this point onwards, you overestimate the population values of y, and behind this, below this point a, before that you underestimate the population values. So your estimate is overestimating here, underestimating here. To summarize, in this video we discussed the concept of population regression function, which was nothing but the values of y using population parameters beta naught plus beta 1 into x. Now beta naught and beta 1 here are the population parameters. Please note, in real life we do not have the luxury of working with population, and therefore this is not observed. This is not observed. So the set of population is not observed, and we only try to map this population or estimate using a much smaller sample, which is called sample. So you work with samples in real life through which you try to make estimates or hypothesis or various predictions about the population, which is much larger in size. When you work with sample, you denote this with a hat symbol, y hat. You do not have actual yi's and xi, you have yi hats, which are the predicted values, beta naught hat plus beta 1 hat into xi. Now please note, this yi hat is the prediction of y. This beta naught is the estimator of population parameter, which was beta naught. Beta 1 hat is the estimator of beta 1, which was the population parameter, and this is called SRF, sample regression function, because it is estimated on a sample which is available at hand, and it tries to estimate the population values, population parameters and population yi's. However, please note, this yi hat is often not very accurate, and it may over predict or under predict the actual values. In this video, we'll discuss a very important class of estimators called ordinary least square estimators. Recall, the sample regression function which we discussed was yi equal to beta naught hat plus beta 1 hat xi plus mu I hat. Here we have removed the hat because now we have also included the error term. Earlier we saw this yi hat equal to beta naught hat plus beta 1 hat into xi, which is nothing but the prediction of yi hat, the predicted value of y hat. Once we add the error term in the prediction, it becomes the actual yi. Now the error term, this mu I hat, or often also referred to as mu I, is important here, because this error term, which is yi minus yi hat or yi minus beta naught hat minus beta 1 times beta 1 hat xi, this error term is an important, very important cost function, and any regression fit or any estimator should minimize some function of this error. In this particular case, the OLS, ordinary least square procedure, as the name suggests, tries to minimize the square of this function, and therefore the best cost function to minimize this can be shown as follows. This is the appropriate cost function, which is the sum of squares of error term, which is yi minus yi hat raised to the power 2 summation. This is our cost function, which is minimized here. Now we can also replace this yi hat using this expression here. So we get yi minus beta naught hat minus beta 1 hat into xi raised to the power 2 summation is our sum of squares. Now we minimize these squared residuals. Question is, why not minimize just the residuals or absolute residuals? Now talking about simple residuals, it fails to recognize the fact that large positive and negative errors, for example plus 6 and minus 6, will tend to cancel each other out. So if there are large deviations, large error terms mu1 I and mu j, which are very large, but on the summation they tend to cancel each other out, simple summation of residuals will ignore that. Similarly, if we are minimizing the absolute residuals, to an extent that is an improvement, because it will recognize that plus 6 and minus 6 or positive and negative residuals should not cancel each other, and therefore large errors, whether positive and negative, they are penalized. However, in case of squared residuals, it penalizes large errors more strongly. So the penalty on large errors is much more stringent in case of squares as compared to simple absolute residuals. To further illustrate and visualize this argument, let's have a look at set of observations plotted on this XY diagram. These are the actual values that we have, rather not population but a sample that we have obtained. Now we try to fit a sample regression function or sample regression, the line corresponding to the sample regression function, which is represented as yi hat equal to beta 1 hat plus beta 2 hat. Now obviously, because we are working with samples, these are estimators. Since these are OLS estimators, we try to minimize the sum of these squared residuals. The difference between the actual values and this fitted line, so this is our sample regression function, the line corresponding to sample regression function. This distance is my error in prediction. Now this error, the larger this error, the problematic it is for me, and therefore a function which minimizes the square of these errors gives higher penalty to large errors as compared to small errors. If I would have added simply the absolute residuals, it would have definitely penalized errors, but a square of residuals penalizes large errors much more than simple absolute summation. Now in this scheme, our final function or square residual summation is this, which we can also write as summation of mu I square is a function, obviously a function of beta naught hat and beta 1, because it is written like this. So it must be a function of beta naught hat and beta 1 hat, which are the key parameters or estimators of importance. So these are sample parameters that we are interested in knowing. Now a very regular simple scheme to minimize this, we want to minimize the squared residuals, we can set the differential of this partial differential with respect to our betas equal to 0. We can set this differential with respect to parameters, different parameter estimates beta naught hat and beta 1 hat equal to 0, and then set the condition of the double differential to positive for minima condition to obtain the estimates of beta naught and beta 1 hat, as we will shortly see. And this is the reason why these estimators are called least square estimators, because we minimize the square residuals, and such scheme or regression model obtained from such scheme is also called Gaussian standard or classical linear regression model, by minimizing these least square errors. Now if you recall, we said that mu I square can be written as this function, which is yi minus beta naught hat minus beta 1 hat xi summation, square summation. We can take the partial differential with respect to beta naught, which is, since it is square term, this is minus 2 times this term, which is same, and then differential of beta naught is nothing but a minus sign, so we get this minus 2 times mu I hat. Why? Because this term itself is yi hat, and yi minus yi hat is nothing but mu I hat, or often referred to as mu I itself. The error, we are interchangeably using mu I hat or mu I here. So this is nothing but minus 2 times mu I, which is the partial differential with respect to beta naught hat. Similarly, we can take partial differential with respect to beta 1 hat, which will be very similar, only that now because beta 1 hat has a multiple of xi, we have an extra xi here. So we have minus 2 times mu I hat into xi summation. This is the partial differential with respect to beta 1 hat. Now we need to set these differential equal to 0 and solve the equation. A closed form solution can be obtained, which is shown here. This closed form solution can be obtained only if certain assumptions are met. Now in this lesson, in a set of series of videos, we will discuss some of these assumptions that are needed, and if these assumptions are met, then we can obtain a closed form solution like this. That means we can precisely estimate the values of beta 1 beta naught and beta naught hat. So we can obtain these beta 1 hat and beta naught hat estimators, and these estimators are often referred to as OLS, ordinary least square estimators, because of the minimization of these residual square scheme. These are called ordinary least square estimators, beta naught hat and beta 1 hat, and once applied to a given sample, we obtain the estimates of population parameters. So what the estimates that we obtain, the beta naught hat and beta 1 hat, based on these formulas, these are the estimates from the sample. To summarize, in this video, we discussed a very important class of estimators called ordinary least square estimators. The ordinary least square estimators are obtained by minimizing the sum of squares of residuals shown by a formula here. To visualize this scheme, we plotted all the observations from our sample like this. Then we try to fit a line, which we often call the line corresponding to the sample regression function because we are working with samples. So this sample regression function line can be written as yi hat because these are only estimate, not the population values, beta 1 hat plus beta 2 hat xi, and then we compute these error terms, that means the difference from these observed values to the predicted values, which is yi minus yi hat. This is the gap, which is called mu I, or we are referring to as mu I hat or mu I interchangeably, and then the square of these mu i's are minimized to obtain the estimators beta 1 hat and beta 2 hat, which are called the OLS estimators. In this video, we'll introduce multiple linear regression algorithm. Recall the simple linear regression problem where there was only one dependent and one independent variable, which was of the following form: b0 plus b1 into x plus error term. Here there was only one independent and one dependent variable x and y. Now all the discussion that we had about the simple two variable bivariate linear regression model, we can extend this to a multiple linear regression very simply as shown here, where y equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on up till beta n xn plus the error term. Here xi's represent the explanatory or independent variables, and their coefficients beta 1, beta 2, beta n are called partial regression coefficients. All that we discussed about the simple bivariate linear regression problem apply to this model as well. All the discussion and properties of simple linear regression model and various other aspects of the regression remain the same, including the properties of error term. That is, this error term is the random stochastic variable with the probability distribution. Now, there are some very important properties of this error term that we need to recall. First and foremost, the expectation of this error term conditioned upon all the independent variables xi equal to 0. That means the mean of this error term given all the xi's is equal to 0 for all the i's. For example, if you remember, for our income and expenditure example where given xi, there were a number of y values. The corresponding error terms, all the mu i's here, this mean of this mu I, the mean of this mu I, that is expectation of this mu I, and since it is for given xi, the conditioned upon xi is equal to 0. Similarly, for all the xi's, x1, x2, xni, the conditional mean of error term is assumed to be 0. Next, no serial correlation or covariance between mu i's. That means for xi, a set of mu i's are there, then for xj, a set of mu j's are there, then the correlation between mu I and mu j's equal to 0. That means these mu I and mu j's are not correlated. That is second very important assumption here. And the third, the variance of mu i's, that is sigma square, is assumed to be constant. That means whatever the variance for this mu I, mu j, or if there was x1, 2 and so on xk's, the error terms are mu k's, the variance of these mu I, mu j or mu k is same as sigma square. That is the third assumption. Next, another very important assumption is that mu I is independent of x's. That means all these independent variable x1, x2 and xn and so on, these are not correlated with error terms. That means correlation or covariance between mu I xi, mu I x2 and so on mu I xn equal to 0. And please also note, the assumption is that model is correctly specified. That means all the relevant influences, that is independent variables xi's, are incorporated in the model. There is no important or variable or factor that is influencing y is left out. Just one caveat, correlation and covariance represent similar property. The normalized version of covariance is correlation itself. if you compute the correlation, if you want to compute the correlation between two variables, you compute their covariance, let's say covariance of x1 and covariance of x2. If you divide them by standard deviation of x1 and standard deviation of x2, you get the correlation between x1 and x2. So this is just a simple information. Another very important condition for this model to work is of collinearity. That is, all these xi's, let's take in together x1, x2 and so on xn, none of xi's can be explained by remaining independent variables. For example, if I take xi, the remaining ones x1 to xi minus 1 and xi plus 2 to xn, they cannot explain this xi completely. That means there cannot be any function which is of this form alpha 1 x1 alpha 2 x2 and so on up till alpha n xn, which is equal to 0. That means any one of these variable cannot be expressed linearly as a linear combination of other independent variables. If that were to happen, this is called perfect multicollinearity. That means if there is a solution to this problem, this equation, this represents multicollinearity. That means one of these xi's can be explained by the remaining independent variables, and in that case of perfect multicollinearity, the model will not run. That is, the equation, this equation will become indeterminate. It cannot be determined. There is no solution. Let's look at the example of collinearity visually. So in this diagram, notice that the independent variables x2 and x3, they have some relationship with y, which is represented by these common areas, but there is no common area between x2 and x3. That means there is no collinearity. However, if there were to exist some common area between x2 and x3, it represents low collinearity. Depending upon this common area, if it increases a lot, like here or here or here, this represents very high levels of collinearity, and this is not good for the estimation. Particularly the fact that if the multicollinearity is not perfect, the previous case that we just discussed, but high, then model will run. The model is not indeterminable. The model can be determined. It is not indeterminate. However, then the problem is that the estimators, for example, beta naughts estimator, beta 1 estimator, these will have very large variances, or what we call standard errors of estimate. Also recall that the significance of these betas is calculated in the form of t statistics and the corresponding p-values. The t-values are simply calculated as coefficient divided by the standard error of estimate, which is basically variance of these estimators. And if these standard error of estimates are very high, which go into denominator, this value is very low. That means your resulting t-values are very low. This means your t-values are very low, and therefore the lower the t-value, the lower are the corresponding p-values, which increases the chances of failure to reject the null hypothesis. That means you will have rather poor confidence interval, more wider confidence interval you need, and therefore even though your R square may be high, which indicates a very good fit in the regression, but still the power of your test will be low, and because of low t-values, and you will be failing to reject the null. That means even the coefficient may be significant, it may be significant, but still you will not be able to say that by rejecting the null. To summarize, in this video we discussed and introduced multiple linear regression model. We noted that all the properties of simple linear regression model apply to this multiple linear regression as well. We also highlighted some important properties of this multiple linear regression model. For example, the conditional mean of error term is 0, which is expectation of mu I given or conditioned upon all the xi 0. We also noted that there should be no correlation between mu i's and mu j's, or set of error terms. We also noted that the variance of these error terms should be constant, which is a very important property called homoscedasticity. We also said that there should be no correlation or covariance between the error term and the independent variables, that is xi's, and it should be equal to 0. The model should be correctly specified. That means all the xi's that are there in the model, there should be no important influence or factor should be left out. Lastly, we also noted the property of multicollinearity. That means none of the independent variables should be explained completely by the remaining independent variable, or all the independent variables should not be expressed as a linear combination which is equal to 0. This leads to perfect multicollinearity, and it makes the model indeterminate. In this video, we'll understand the interpretation of various aspects of multiple linear regression algorithm. Similar to our understanding of two variable or bivariate regression model, this expression here represents the conditional mean or expected value of y given the values of x1, x2 and xn and so on. So this is very similar to the expression that we saw earlier, expected value of y given x. Here, instead of single independent variable, we are considering all the independent variables from x1 to x1, and therefore this represents the expected value of yi given all the xi's. This is called the conditional mean or expected value of y given the fixed values of xi's or conditioned upon the fixed values of xi. Notice the coefficients beta 1, beta 2 and so on up till beta n here. These are called partial coefficients. For example, this beta 1 is the partial coefficient and it measures the effect of x1 on this variable y net of any effect from any other explanatory variables, that is xi, or in other words, keeping all the other xi's constant. If all the xi's are held constant except x1, then beta 1 will represent the impact of x1 on y. Let us introduce a very important parameter, which is r square. This r square represents the part of variation of variable y which is explained by this model. I repeat, this r square represents the variation or variance in the variable y, which is the dependent variable, which can be explained by the model. This all the xi's and coefficients to put together. The computation is very simple. Basically, this is explained sum of squares divided by total sum of square, which is equal to 1 minus residual sum of squares upon total sum of squares. Let me give you a little bit background on this. Recall that the values of y on xy axis are provided like this, and this is your fitted line. So this is the total, let's say this is yi, then this is the total gap. Sum of squares of these total yi's will be total sum of squares. However, this much part is explained. This much part is explained part. So this squares of these distances would be explained sum of squares, and this is unexplained part. These are the error terms. So this is unexplained or residual sum of squares. So here explained sum of square, that means these sum of squares divided by total sum of squares, which are these total terms. Total sum of squares is the explained part, ratio of explained part. This can also be computed as 1 minus residual sum of squares upon total sum of squares, where the sum of squares of these distances is called residuals. This remains same whether we are talking about bivariate regression or multivariate regression, as we are seeing here. A more improved version is also computed in the form of adjusted R square, where a small adjustment is made. Here, instead of using RSS and TSS, we divide these residual sum of squares and total sum squares by their respective degrees of freedom. For RSS, the degrees of freedom are n minus k. Here, n is the total number of variables. Here, n is the total number of observations in the sample. K is the number of coefficients excluding beta naught. So all the beta 1 to beta n, all the coefficients excluding beta naught, divided by n minus 1. N minus 1 is the degrees of freedom for TSS. So I repeat, RSS upon n minus k, where residual sum of squares has n minus k degrees of freedom, where n is the total number of observations in the sample and k is the coefficients from beta 1 to beta n, and TSS divided by n minus 1 degrees of freedom, where n is the total observations. This is often referred to as mean sum of squares of RSS, mean sum of squares of RSS, that is residual sum of squares, and mean sum of square of TSS, that is total sum of squares. Now, these n minus k and n minus 1 are called degrees of freedom. Please notice this adjusted R square is very interesting entity here. If we rearrange the expression for R square and adjusted R square, we get something like this. Please notice in R square, in this expression, we are putting a certain additional penalty in the form of these n minus 1 upon n minus k. That means the more the number of variables, the more the number of these k's or variables in the model, this R square is penalized in the computation of adjusted R square. That means The more the number of k's, the lower the value of adjusted R square. So there is certain penalty that this expression puts on R square, and therefore this adjusted R square, which is after adjusting for these degrees of freedom, it puts a certain penalty for addition of variables. The reason being, the normal R square can be easily inflated just by adding the number of variables, small variables where the contribution to the explanatory power is so low that they are not very important, but still if their numbers are too large, the R square value is inflated. So this penal term, this penalty is inflicted on this computation, so that there is a trade-off for adding more variables, which in the form of explanatory power to the model as well as this penalty, and therefore the resulting expression adjusted R square would identify whether the addition of variable is important or not. Lastly, another very important aspect of this model is the coefficients or estimates of the coefficients. Beta naught hat and beta 1 hat, these are simply the estimates of the coefficients using OLS estimators. Based on OLS estimators, these estimates are made. These estimates have some variance. So in repeated samples, these estimates have variances, and the square root of the variance of these estimated parameters indicates the error in estimation or standard error of the estimate. So if you have repeated samples, these beta naughts will have a distribution. Estimates of beta naught will have a distribution, and higher the standard error of this estimate or the variance of this estimate, poor the estimator. Remember, we said that T statistic, which was very important, is coefficient upon standard error of estimate. The higher the standard error of estimate, the lower its T value and lower its significance in the regression model. So for us, the better model or better estimator where SE is lowest, standard error is lowest, given certain assumptions that we made earlier about heteroscedasticity, autocorrelation, multicollinearity, and so on, OLS estimators are supposedly the best in class estimators available with us. And that is why we discussed OLS estimators in great detail. To summarize, in this video, we discussed the interpretation of multiple linear regression. We noted that the expressions such as conditional expectation of the dependent variable remains similar as bivariate regression model. The interpretation of coefficient is also very simple. These are simply partial coefficients which reflect the impact of a corresponding variable on the dependent variable, keeping all the variables constant. We also discussed the computation of R square measure and adjusted R square measure. We noted that adjusted R square measure provides slightly improved version of R square where we adjust for addition of more variables, and therefore it recognizes the fact that addition of more variables simply just to increase the explanatory power is not desirable, and therefore it puts a penalty or a penalizing adjustment to reflect that variables should contribute significantly and not just in small explanatory power. We also noted that it is desirable that the estimators of the coefficient like beta naught hat and beta 1 hat, these estimators should have lower variance. That means their standard error of the estimate should be lower, which increases the power of the estimate or power of the regression, so that the t values and therefore the ability to reject the null and bring out its impact on the model more efficiently. So for that, we need estimators with lower standard errors. In this backdrop, OLS estimators are considered to be the best estimators as they offer the lowest variance in the entire class of linear estimators. In this video, we'll briefly review the key assumptions behind the CLRM, that is classical linear regression model. The Gaussian standard or classical linear regression model as it is called makes 10 very important assumptions. The first assumption is that the linear regression model is linear in the sense it is linear in parameters. For example, let us look at these three diagrams. This one, y equal to beta 1 plus beta 2x plus beta 3x square, is linear in parameters but non-linear in variables, which is x square term. However, it can be estimated with the CLRM because it is linear in parameters. On the contrary, this one, y equal to e to the power beta 1 plus beta 2x, is non-linear in parameters. Although there are transformations, as we'll see, that can make this expression linear, but as of now it is non-linear in parameters. Look at this expression. Earlier we had a quadratic expression where x square term was there. Here we have x cube term, but still it is linear in parameters and therefore directly estimated. It can be directly estimated through classical linear regression model. Second assumption here is that the values of x in repeated samples are fixed. That means they are not stochastic, and they do not have any random component. So they are fixed in nature. Unlike y or error term, they are not stochastic. They don't have any probabilistic distribution. They are fixed and estimated with certainty. There is no stochastic aspects of x. Next, and a very important assumption is that zero conditional mean of the disturbance term mu I, or the expected value of disturbance term mu I or error term is zero conditioned upon each xi. For example, let's say we have x1 variable corresponding to which there are number of y's, and for all these y's, error terms mu1 i's would be estimated. Mu1, all these mu i's, if we take the mean of these mu i's, since it is for only x1, then mu I x1 equal to 0. Similarly, for x2, all the mu i's, mu1 I, mu1 2, mu2 2, and so on, all these mu i's will be 0. So conditional mean of all these error terms for given xi should be equal to 0. The next assumption, assumption number 4, is of homoscedasticity or equal variance of these error terms. So like we said earlier, for a given value of x, the variance of mu I is same for all the xi's. That is, conditional variances of mu I are identical. That is, expected value of mu I minus expected value of mu I xi raised to the power 2 is constant and equal to sigma square. If they are not constant, that means they are varying with xi's. For each xi the variance is sigma square, then this is called heteroscedastic variance, and it creates problems. That means the solution that we obtain for beta naught hat, the closed form solution that we obtain for beta naught hat and beta 1 hat and so on and so forth for other coefficients will not remain valid. Look at this diagram here. Here, with the assumption of homoscedasticity, the variance of error term for each x are same. Notice, for each xi, the variance of error terms is same. However, here the variances are different for different xi's, and therefore it has heteroscedastic variance of error term. In this particular case, the solution, the closed form solution for coefficients beta I hat that we obtained earlier, we saw earlier for the simple linear regression, will not remain valid. Another very important assumption, assumption number 5, is the no autocorrelation between the disturbances or error terms. So for any two values of xi and xj where I equal to not j, there is the correlation between mu i's which are corresponding to xi and mu j's which are corresponding to xj should be 0. In symbolic terms, mu I and mu j, the covariance between mu I and mu j, given xi xj, which is also equal to expectations of this expression into this expression whole square, or expectation of mu I given xi into mu j given xj, because this expectation is anyway 0, expectation of mu I 0 and mu j is also 0, so this simplifies to mu I given xi and mu j given xj, and this is equal to 0, which is also a way of saying that correlation between mu I mu j given xi xj is 0. So this can also be said, because correlation is nothing but normalized or standardized form of covariance. So we can say that covariance between mu I mu j is 0 given xi xj, or correlation between mu I mu j is 0 given xi xj. If there is some correlation, then that can also be examined visually before going to the mathematics of it. For example, if there is no autocorrelation, then the error terms will be plotted randomly without any pattern. If there is positive autocorrelation, then error terms will plot like this with each other. It indicates positive correlation. And if it is plotted like this, then it indicates a negative correlation between error terms, that is mu I and mu j's. Assumption number 6, another very important assumption, is that mu I, the error terms, and xi are not correlated. This is very intuitive assumption because we said xi is fixed, it is not stochastic, it is taken from outside and is not getting affected by the process. So mu I, which if the model is correctly specified, all the relevant influences are taken with xi's, mu I should not be correlated with xi, which is to suggest that covariance between mu I and xi, which is represented as this term, expected value of mu I into expected mu I and xi minus expected value of xi, this should be equal to 0. Notice here we already know that the expected value of mu I, this is 0 already. So this expression simply becomes covariance of mu I xi simply becomes expectations of mu xi, which is this term, which is 0, which in simple terms says that correlation between mu I and xi is 0, because like we said earlier, correlation is nothing but standardized form of covariance. So mu I and xi are not correlated, which is our assumption 6. Then the remaining assumptions are quite intuitive as well. These remaining 4 assumptions are assumptions 7, 8, 9, 10. The 7th being the number of observations must be greater than the number of parameters to be estimated. In fact, for a better estimation, the number of observations should be much larger than the parameters to be estimated. A good thumb rule should be that number of observations should be at least 5 times the number of parameters. The x values, the independent variable must have some finite variance. For example, if the variance is very low or if all the x values are almost same, then the model cannot be estimated, or even if estimated, the estimates are very poor. The regression model is correctly specified, which means all the relevant influences, that is the x size, are taken in the model, and those that are left or not considered should be very small, that even if they are mixed with the error term, because we are not accounting for them specifically in the model, they should not create any trouble in estimation. Lastly, there is no perfect multicollinearity. That means there should be no perfect relationship between the independent variables of this form. So if it is of this form, this indicates that one of the independent variables can be perfectly explained by the remaining variable, and in this case the model will be indeterminable. It cannot be determined. To summarize, in this video, we reviewed and examined all the key 10 very important assumptions of classical linear regression model. In this video, we'll introduce blue properties of OLS estimators. OLS estimators are often considered to be as best linear, unbiased, and efficient estimators. These are called blue properties. We already know that OLS estimators are linear in parameters. In addition, there are two very important properties, that is unbiased and efficient. Let us start with the unbiased estimators. Any estimator that has its expected value same as the true population parameter. For example, if we are trying to estimate beta 1 using some estimator beta 1 hat like OLS estimator, and if the expected value of this beta 1 hat in large repeated samples, if in repeated samples the expected value of beta 1 hat is same as the true population, then it is called unbiased estimator. However, if the expected value is different, for example this curve, notice this, if the beta distribution, the distribution of the coefficient here and expected value is somewhere here, which is different from the true beta, then this is unbiased estimator. In contrast, the blue one, this one, is called unbiased because its expected value is somewhere around true beta, and such estimators are often called unbiased estimators. It is considered that if certain assumptions that we discussed regarding multicollinearity, autocorrelation, heteroscedasticity, the 10 classical assumptions, if they are held, then OLS estimators are considered as unbiased estimators. Next, we have efficient versus inefficient estimators. Estimators with very low variance or standard error. Standard is nothing but the variance of estimator. So if the variance of estimator is low, it is called relatively efficient. In this figure, this estimator has a lower variance, lower standard error as compared to the dotted one. The solid blue line has lower variance as compared to dotted one, and therefore it would be considered as more efficient as compared to this. Across different classes of estimators, OLS estimators are said to be best in terms of their efficiency. That means they have the lowest standard error of the estimate. If these two properties of unbiased and efficiency are combined, it is said that for OLS estimators in large samples, their expected value converges closer and closer to the true beta, and they become more and more efficient. That means their variance becomes lower and lower, and therefore the combined property of efficiency and unbiasedness is often referred to as consistency. What is consistency here? Consistency is that in large samples, the expected value and the expected value and variance converge to true beta. That means the estimate converges to true beta. Its expected value becomes closer to true beta and its variance comes lower and lower. So essentially it converges to true beta in large samples, which is called the consistency. Combining these properties, OLS estimators are best in class, and therefore they are often referred to as best linear, unbiased and efficient estimates. To summarize, in this video, we discussed the blue property of OLS estimators. We noted that across all the samples, across all the estimators, OLS estimators are best linear unbiased estimators, and combining the property of unbiasedness and efficiency, they are consistent estimators as well. That is, in large samples, the sample estimates converge to population parameters. Classical linear regression model, CLRM, and hypothesis testing part 1. In this video, we'll introduce the normal distribution and its application in classical linear regression model for hypothesis testing and estimating the significance of coefficients or parameter estimates. Recall the discussion on normal distribution. A simple normal distribution on returns have daily price changes or returns on the x-axis here, on the horizontal x-axis, and on y-axis we may have frequency of days or percentage of days. A fitted normal distribution would look something like this green bell-shaped curve. While the bars are actual returns, the continuous shaped normal distribution can be superimposed on this. The important aspect of normal distribution is that it can be simply defined by two parameters. One is the mean, which is mu, and its variance, sigma square, where sigma is the standard deviation. Using just these two parameters, we can define a normal distribution, and as we will see in this video, the application of normal distribution considerably improves the quality of analysis or regression analysis with hypothesis testing and estimation of significance of parameter estimates. A version of normal distribution which is most often employed is called standard normal distribution. Most of the properties of normal distribution, in fact all the properties, remain similar, except that on x-axis, instead of the actual values, say returns, we use the scaled or normalized or standardized return, that is x, which is the value of return, minus mean upon standard deviation. So it is normalized so that its mean is 0, mean of 0, this distribution will have a mean of 0, and standard deviation of 1 because of this transformation. On the y-axis, instead of frequency or percentage frequency, we use something called probabilities, or rather probability densities. So for example, each point will represent a particular standardized return in Z form, and on y-axis we'll have the corresponding probability, which is essentially a probability density, the probability corresponding to this point, which is essentially nothing but probability density. So it would make more sense to have a segment of strip on the x-axis. So the area will represent the probability of observing return in this window, which is represented by a z interval from x1 to x2, where x1 and x2 can be mapped to certain return. For example, from z or -1 to +1, that is in terms of standard deviation, this essentially represents the standard deviation form of returns. So -1 to +1 standard deviation, we have 68.26% of return, ±2 standard deviation area, that is 95.44% of the probability will lie within ±2 standard deviation, and within ±3 standard deviation we have 99.74%, and this is irrespective of different returns because this is now in standardized form. So we can simply say that within if it follows normal distribution, then as per standard normal distribution, irrespective of mean, the mean and standard deviation can be anything. If it follows normal distribution, then for standard normal distribution, these properties will be held no matter what are the mean and standard deviation. That means within ±3 standard deviation you have 99.74% of the probability, within ±2% you have 95.44% probability, and within ±1% there's 60.26% probability that observations will lie within this. Now with this introduction of normal distribution, we can apply the hypothesis testing concept on our parameter estimates beta naught hat and beta 1 hat, because hypothesis testing and inference inferential statistics are required for sample parameters, we need to draw inferences about population parameters using these sample estimates of beta naught hat and beta 1 hat. And more clearly, to be more precise, we would like the estimated parameters, these beta naught hat and beta 1 hat, to be as close as possible to the population parameters, that is beta 1 and beta naught. Now, please remember why these beta naught hat and beta 1 hat are different from beta naught beta 1, because in repeated samples, these beta naught hat and beta 1 hat will be different because there is certain randomness introduced because this error term. So this error term introduces randomness in the model, and because of that the estimates are not same as population parameters. Every time you change the sample, you will obtain certain different beta naught hat and beta 1 hat and other population parameters. Please note, because this randomness is introduced by this error term, the sample coefficient estimates, that is beta naught hat and beta 1 hat, will also have a probability distribution, and this probability distribution will be similar to the error term because this randomness is introduced by this error term itself. And therefore every time you change the sample, you will obtain different estimates of beta naught hat and beta 1 hat. And therefore, if you want to make any inference about beta naught hat and beta 1 hat, you need to know their distribution, which is essentially the distribution of the error term itself, because this is the one causing randomness in beta naught hat and beta 1. So we make the following assumption about the error term in the model. Remember the simple model y equal to beta, this model which we extended to multiple linear regression, where this mu was the error term. So the following assumptions are made about this error term. First, the expectations of this error term or the mean of this error term is 0 first. Second, we assume that the variance, that is expected value of mu I minus expected mu I square, or this, because this is 0, is same as sigma square. So this is homoscedasticity. The variance of error term is constant. Second, the covariance or correlation between mu I and mu j, because this is 0, it converges to this expression, is also 0. That means mu I and mu j across observations I and j are not correlated. Combined, the assumption can be written as in this form, that is mu I is distributed normally with a mean of 0 and variance of sigma square with the 0 autocorrelation. Please note that normal distributions, like we said, are very easily defined just by two parameters. One is the mean mu and variance sigma square. Now, as we have made the normality assumption and previous other classical linear regression model assumptions that we discussed, 10 assumptions plus normality, OLS estimates are blue estimates, that is they are best linear, unbiased, efficient and consistent estimates, as we discussed in the previous video. And these, therefore, since they are consistent, these estimates converge to their true population values as sample size increases. The model, as we have already seen, yi equal to beta naught hat plus beta 1 hat xi plus mu I hat. Here, the predicted values of yi are written as yi hat, which is beta naught hat plus beta 1 hat into xi. Now, please note, the mean of, it is assumed that the mean of beta 1 hat or expected value of beta 1 hat is same as the population parameter, because if these assumptions are held, then the expected value of beta 1 hat is same as beta 1, and variance of beta 1 is sigma beta 1 square. And to summarize these two definitions, we have beta 1 hat distributed normally. So this represents that beta 1 hat is distributed normally, and its mean is beta 1 and its variance is sigma square beta 1 hat. So this is the combined expression for these assumptions. Now we can also translate these assumptions that we discussed in the previous slide in the standard normal distribution format. Recall that this z, or the standard normal version, is the value itself beta 1 hat minus its mean, which is the estimate of population. This is expected to be same as population parameter. So beta 1 hat minus its mean divided by standard deviation of beta 1 is the standardized version, which is z. And like we said, this z is distributed normally with a 0 mean or expected value and a variance which is 1, because it is the standardized version. So it is normally distributed with a mean of 0 and standard deviation of 1, and it helps us in doing any kind of hypothesis testing and inferential statistics. To summarize, in this video we introduced the normality assumption with error term. Since the error terms are the ones introducing randomness in the population parameter estimates or sample estimates, therefore the sample estimate itself is normally distributed. the beta 1 hat, beta naught hats, sample estimates. Normal distribution, because normal distributions are very easily defined with just two parameters, that is mean and variance. And if these assumptions are held, then the expected value of beta 1 hat is same as beta 1, which is the population parameter. So the sample estimate converges to population parameter estimate if the assumptions are held, as we discussed. The classical normal linear regression model assumptions are held. Its variance is variance of beta 1 hat, which we called as sigma square beta 1 hat, and which is this sigma square beta 1 hat, and therefore we said that beta 1 hat is normally distributed with the mean of beta 1 and variance of sigma square beta 1 hat. We also saw that in standardized form, this is represented by the statistic Tz, which is, since it is standardized with this formula, it has a mean of 0 and a variance of 1 and distributed normally. In the next video, we'll see the application of this normal distribution and conclude its role in hypothesis testing and making inferences about the coefficient. In this video, we'll conclude our discussion on hypothesis testing with classical normal linear regression model. Please remember, in repeated sampling, the point estimate, that is beta 1 hat, converges to population parameter, which is beta 1. This is to suggest that if you have number of samples, the mean of beta 1 hat will converge to two population parameter beta 1. However, we do not have the luxury of working with many samples, and often we are left with one sample. Even that is a very small sample as compared to the overall population. And therefore, the accuracy of this point estimate of this beta 1 hat is important. How reliable is this estimate? Because this single estimate definitely differs from the true population parameter. And therefore, the reliability of this estimate is measured by standard error. Please recall that in OLS estimation of regression model, each parameter estimate, that is, for example, beta naught hat or beta 1 hat, is estimated with some error. The square root of the variance of this estimated parameter indicates that error in estimation, or essentially the precision of that estimate. So the variance of this parameter estimate, we take the square root of that, which becomes the standard error of this estimate. Let us examine how this standard error plays a very important role in hypothesis testing and confidence interval estimation around this coefficient. In the hypothesis testing procedure, you set up a confidence interval. For example, let's say you want to be 95% confident in your estimate of that coefficient or parameter estimate. Then there is a 5% possibility or 5% chance you are willing to take where you may be wrong. And therefore, if you have taken this 95% region of confidence you are considering, then the remaining 5%, which is distributed in two half regions, 5% divided by 2 and 5% divided by 2, which is 2.5%, is called critical region or region of significance where you may be mistaken. So this is the region which you are willing to take a chance where you may be mistaken. 2.5% on the right and 2.5% on the left, which is overall 5%, because you have taken you are willing to take a 95% confidence. Let's see how this works in the case of regression. Let us say you hypothesize the population parameter as beta 1, which means if it is a simple linear regression model, you are estimating a regression like this: beta naught plus beta 1 into x, and you estimate a coefficient of beta 1. Now, the way the convention suggests you consider this beta 1 or hypothesize it to be 0, which has a practical implication that if beta 1 is 0, x, our variable of interest, has no impact on y. This is how the convention works. So you assume that you start with the hypothesis that beta 1 is the 0, or your true population parameter is 0, which means x does not affect y. Now you want to set up a 95% confidence interval. And therefore, if you want to set up a 95% confidence interval, which is 1 minus alpha, your alpha or significance level is 5%. So you set up a 95% confidence interval around your population estimate beta 1, which is 0. You set up this confidence interval and you are willing to take a 5% chance, 2.5% on the left and 2.5% on the right, that you may be wrong as well. Practically, you are assuming that beta 1 is 0, that means x does not affect y. So this is your essentially your null hypothesis. And if this null is rejected, you consider a null that beta 1 is 0, and if your estimate falls in this region, you tend to not reject your null. However, if your estimate falls in this region, which is the significance region or critical region, then you reject the null and say that beta 1 is not 0, it is significant, and the implication is that x indeed affects y. So there is a relationship between x and y if you are able to reject the null. Now, in practice, along with 95%, we also check the significance with 90% and 99%. That means this value, in case of 90%, this value is 5% on the left and 5% on the right. In case of 99%, it is 0.5% on the left and 0.5% on the right. That means 1% significance. Now that we have seen standard normal distribution, we also know that if this is a normal distribution, then for each value of probability, whether it is 5%, 2.5%, we have a z value. So depending upon the area in this region, we can find a relevant z value corresponding to each point that we have already seen. In practice, we have small samples, and often population variances are not known. So instead of using z parameter, we make use of student's t distribution, which is very similar to standard normal distribution. Only minor difference is that student's t distribution has relatively fatter tails. It has fat tails, which means for any hypothesis testing, rejection of null requires more evidence. So it needs more evidence to reject the null, and therefore because we work with small samples and we do not want to make any major mistakes, we tend to work with student's t distribution. However, the procedure remains exactly similar. Whether you use standard normal distribution or student's t distribution, the procedure is exactly similar. However, in practice, we tend to do hypothesis testing with regression coefficients using student's t distribution, as we'll see in our practice example, because it requires more evidence to reject the null, and therefore if we are rejecting the null, we are more confident. So we try to find the corresponding t value corresponding to this alpha value. We try to find this t value, which is on this side. Left side it is minus t alpha by t by 2 or plus t alpha by 2. Alpha by 2 indicates that this t value is corresponding to alpha by 2. So in the t table, t statistic table, we take the values which are corresponding to plus alpha by 2 and minus alpha by 2. They are same because of symmetry in the distribution, they are same. Now the way it is done, you compute the relevant t values. You compute the relevant t values or critical t values corresponding to these alpha by 2. For example, if alpha is 5, then you compute the t value corresponding to 2.5% level on the left side and 97.5% on the positive side, right side. So you compute t values corresponding t values. These are called critical t values, which is plus minus t alpha by 2. One for 2.5% on this side, critical value, and one for 97.5. This is in the case of 95% confidence interval. You can find the relevant values similarly for the 90% or 99% level of confidence. Once you compute these critical or significant t values, you compare them with the t value that is obtained in the sample. So you compute a sample t value which is there for your sample, and you compute if this t values is larger than this plus minus t alpha by 2, that means it falls on the right side, either on the right side in the critical region or on the left side of the critical region, then you reject the null. That means you say that beta estimate of beta 1 hat or beta 2 hat or whatever is estimate is under consideration, it is significantly different from 0. It is not equal to 0. If it is on this side, that means it is negative, and if it is on this side, right side, it is positive, but it is significantly different from 0. That means it is not 0. And therefore we are rejecting our null and saying with that level, let's say in this case 95% confidence or 5% significance, that beta 1 is significant and x, the variable of interest, indeed affects the dependent variable y. So just to summarize the discussion, you assume a null hypothesis which is called H naught, that the true population parameter beta 1, which is assumed to be 0 in most of the cases, and therefore your alternate hypothesis H1 is that true population parameter beta 1 is not equal to 0, or the variable of interest, which is xi, indeed affects the variable y. The decision rule here goes like this. You construct a confidence level of 1 minus alpha, where alpha is 5%, the level of significance. So your confidence interval is 95% for the population parameter beta 1. Then you compute the relevant t statistic corresponding to this critical value of alpha by 2 on this side, and here alpha by 2 on this side. So you compute the critical t value. So let's call on this side, this is minus t alpha by 2, this will be negative. So for example, for 95%, here the relevant t statistic will be corresponding to a 2.5% value, and on the right side it will be corresponding to a 97.5% value. If your computed t statistic for the coefficient, if the computed t statistic, which is beta 1 estimate of beta 1 minus 0 upon its standard deviation of beta 1 hat, this number, this is the t statistic that you compute for the sample, if it is greater than or falls in this region, greater than this value or lower than this value and fall in this region, then you reject the null H naught. You don't say that I accept the null, but you reject the null. You reject the null or fail to reject the null. You don't say that you accept the null. Either you say I fail to reject the null or you reject the null. So if you reject the null, then you say that this variable affects y. If you fail to reject the null, that means your parameters fall in this confidence region. Then you fail to reject the null and say x does not affect y. In this video, we'll discuss some of the other functional forms of OLS regression that are nonlinear in nature, and we'll also discuss how to transform them for suitable estimation with OLS regression procedure. To begin with, we'll have a look at some of the log linear or log-log formations. For example, have a look at this expression yi equal to beta 1 times xi to the power beta 2 into e to the power mu I. Now, in order to estimate this, notice the parameters are of nonlinear form, and therefore if we take the natural log transformation of this expression on both sides, left hand side and the right hand side, on the left hand side we have ln yi, on the right hand side we have ln of beta 1 plus beta 2 times ln of xi plus mu I, which can be further transformed into yi dash equal to alpha plus beta 2 times xi dash plus mu I. Now this final transformed model, notice it is linear in parameters alpha and beta 2, and therefore if we estimate this model through OLS regression procedure, the interpretation of beta 2 here is important, which is of coefficient of interest, which is beta 2 measures the percentage change in yi for a percentage change in xi. Because this is log-log transformation, that is why it is percentage change in yi for a given percentage change in xi. But for all times to come, remember that the original nature of equation has transformed. So if you wanted to estimate this beta 2, the interpretation with respect to original xi and this xi dash is different. Nonetheless, this expression can be estimated with the OLS regression procedure. Now have a look at this another expression for which we are going to use log-lin transformation, yt equal to y naught plus 1 plus r raised to the power t. If we take the natural log and transform the model as below, here natural log of yt equal to beta 1 plus t times beta 2, because it was 1 plus r to the power t, the logarithm transformation has made it in this form. Now please note, this is a semi-log model because the dependent variable yt is in log form while the independent variable t is not in log form, and therefore the interpretation of beta 2 is as follows. Beta 2 measures percentage or proportional change in yt for a given absolute change in t. However, if your coefficient of interest were y naught and 1 plus r, the interpretation is not exactly identical to them. Nonetheless, this model can be transformed with the help of OLS procedure. Also, this was a log-lin transformation, a vice versa interpretation for lin-log model, as we can see here, that is given change, absolute change in yt for a percentage change in xt will be applicable to a model of this kind, where xt, the dependent variable, is in the log form, while yt, the independent variable, is not in log form, and therefore the interpretation of beta 2 will be, like we said, absolute change in yt for a percentage or relative change in xt. To summarize this video, we noted that there are certain expressions which are not exactly linear in parameters. However, with some transformation such as taking log on both sides can transform them into different or resulting format which is linear in parameters, and therefore the resulting format or the transformed expression can be estimated using OLS regression procedure. However, the interpretation of coefficient from this transformed equation may not be identical to the original equation. Nonetheless, it is still useful for estimating the coefficients and making policy decisions and from such perspectives. Among supervised learning algorithms, regression algorithm is a very important tool employed in finance domain for applications such as forecasting security prices or credit scoring. Regression algorithms can be run with only two variables, one independent and one dependent, which is known as simple linear regression, or with more than two variables, which is called as multiple linear regression. The key variables in a regression model include a dependent variable, one or more independent variables, coefficients of these variables, and an error term. The error term accounts for the variation in the dependent variable that cannot be explained by the model. While regression analysis can provide the statistical significance of the relationship, the direction of causality should come a priori from the theoretical underpinnings. Refer to the rain versus crop example in this lesson. Ordinary least square or OLS is the most often employed method to estimate a regression model, which involves minimizing residual sum of squares. OLS estimation or ordinary least square estimation of regression involves 10 key assumptions. The most important assumptions here include linearity in parameters, exogeneity of independent variables, zero conditional mean of the error or residual term, homoscedasticity of error variances, absence of multicollinearity, no autocorrelation across error terms, no correlation between error and dependent variables. If these assumptions are held, then OLS estimators are referred to as blue, that is best linear, unbiased and efficient estimates. The statistical significance of OLS estimators is determined through hypothesis testing of coefficients individually. This requires normality assumption of the error, that is residuals. Very often, the model is not linear and may require some kind of transformation to make it linear, which can be subsequently estimated through OLS. However, the interpretation of coefficients also change with such transformations.